For this tutorial, I'm going to cover the other three basic data structures: the queue, the dequeue, and the list. A queue is very similar to a stack. The only difference is, instead of taking from the first position and removing from the, or adding to the first position and taking from the first position, like what the stack did, it inserted right in front of that pointer that represented the stack and then it took out right behind that pointer. A queue inserts into the very last position and takes from the very first position. So if you were to code one really fast, struct queue extends array and struct, and then let's go ahead and do our on init. To make it clear, first we're going to need our little next thing. So there's the next, and that's just the items pointing to each other, so whatever's next. It does only iterate forward. It's what's called a singly linked list, because it only points one way. Next thing we'll probably need is a first. So in this case, first is 0. And really, the first next is queue.next. That will actually be the first, so we don't really need that, actually. But what we do need is a last, because as you see, there's no way to get the last thing unless you loop through the entire queue. So we should probably have something pointing to the last thing in the queue. Now to start with, let's implement that alloc module that we did before. I actually put it up here in the core. So there it is. And now for create, we're going to initialize the queue. So first local this type this equal allocate, then return this. Now to initialize the queue, this variable right here, this value, is going to be the pointer of the queue. So it's going to be the very first node in the queue, the very first value. This value is never destroyed until the entire queue is destroyed. You don't pop it off, you never read it, it doesn't have an actual value to it, it's just there. Initializing it, the first thing we want to do is we want to set last equal to that first value, because that's the first node in the queue. And then we want to set next equals 0, because there's nothing after that first node. Now you're going to see why we want to set the last to that first value in a second here. So for the add method, let's make it take an integer node, so people can use the allocate method up here to allocate their own nodes, and then return nothing, end method. What we're going to do here is put the node at the very end of the queue. So set next last equal node, and then set last equal node. That's all there is to it. So notice here right now last is the queue instance. So the next, the very first pointer in the queue ends up being set to the node, and then last gets updated to the node. Then if you want to add another node, set next first node equals second node, set last equals second node, and so on and so on. So it just keeps forming up in order from when they were added. First the queue, then node 1, node 2, node 3, node 4, etc., etc. When you take from the queue, it's a lot like taking from the stack. So method remove takes nothing, returns this type. And in fact, let's call this pop, since it's the same operation. All that happens is set next queue equal to next queue. And in fact, because we want to return this value, let's go ahead and get the node here. Local this type node is equal to next queue. Set next queue equal to next node, and then return the node. So it is identical to the stack pop operation. The only thing that is different is the add operation. Instead of adding right in front of the queue, you're adding to the last position. So what this should essentially do is add items to the end of the queue, like queue node 1, node 2, node 3, node 4, and then take from the front of the queue. So queue node 2, node 3, node 4, then queue node 3, node 4, and etc. Now at the very end, what will end up happening is last will be, in fact, last will still be this last node here when the queue becomes empty. So what we need to do is say if next queue is equal to 0, then set last equal queue. So if the queue is completely empty now, update the last back to the queue itself. That way when you put stuff back in, it won't be put behind this whatever that node was. And so now how about an example? Local this type queue is equal to queue.create. And we're missing a destroy method here. So let's go ahead and write that really fast. Method destroy takes nothing, returns nothing, end method. And what this is going to do is loop through the entire queue. So set and deallocate every element. So deallocate this, set this equal to next this, exit when 0 equal this. And that's all there is to it. And that will deallocate every single node in the queue. Now, what normally happens is we allocate the nodes ourselves. So let's go ahead and, from now on, allocate this actual node. Local this type node equal allocate, and there we go. And we don't return it. It normally takes something like a value, for example. So let's go ahead and add a value here. Read only integer. In fact, we can make that private integer value. Let's make it read only. That way people can loop through the queue if they want to. And then we can update that later so that people can loop through. Then we do not, well, we return the value instead. So right there, the value. So return, so we're going to call node.deallocate, and I should probably fix this right here. There we go. And then we're going to return node.value. Now normally in the pop command we don't return anything. If people want a value, they loop through it or they read the very first value in the queue. But for now we're going to do it the standard C++, C, etc. way, and we're going to require you to actually get the value via popping and adding. And actually in C++, this is still called the push command. It's called push back or something crazy like that. Let's keep that as add. So now we have a way to destroy it, a way to pop from it, and a way to add to it, and then of course a way to create it. And to try it out, we're going to try pushing some values there. Call q.add 1, q.add 2, q.add 3, q.add 4, q.add 5, and call q.add 6. And now what we're going to do is loop and loop and exit when, in fact, we should probably do if next queue not equal, or rather, if node not equal 0, then call node.deallocate. That would be better. So exit when here we'll have a value here too. Local integer value. So we're going to set value equal q.pop and exit one value equals 0. And then for this value we're going to call print I2S value. And what this should do is print 1, 2, 3, 4, 5, and then 6. And then at the very end here we'll call q.destroy, which will just end up deallocating this first pointer right here. Oh, I had a little typo there, didn't I? Right there. And another typo there. Next, this. Lots of typos, actually. Okay, now it's set to go. And nothing happened. Oh, I know why. Because we never set the node.value here. Set node.value equal value. Okay. Now it will work. 1, 2, 3, 4, 5, 6. So it worked perfectly. Notice that these elements don't have to be sequential at all. They are pointed to with the next array. Now how it's normally done is we don't do a private stack integer array here. We do a read-only integer and read-only this type next. Then we get rid of that. So local this type this equal allocate, set next equals 0, set, and here we change this to a this type. So set last.next equal node, set last equal node. Then set next equal to node.next. If next equals 0, set last equal this. Node not equal 0, okay. Set this equal next. And now instead of the pop, we can do the normal return nothing here. So all we'll literally do here is we'll change this into a, we'll keep that as pop, and we'll just have a set next equal to, in fact, we'll change this around quite a bit. We'll have a if next not equal 0, call next.deallocate, and then set next equal to next.next. And there's the pop. And let's also put this in here. And that should do it. And now when we want to iterate over everything, we can do it this way, and we probably want to do read-only integer value. And now we can do the q.add and change this to local this type node. So we do set node equal q.next, exit when node equals 0. So now we're comparing pointers here, struct instances, so this is a valid thing right here. If what we had before, we could have had a 0 value in the queue and that would have exited prematurely. And then we can call I2S print node.value, and then here we can still have our q.destroy, and that'll work correctly. And there we go. It prints 1 every time, probably because I didn't change this to node.next. Okay. So notice I set the node to the queue itself, and now I'm arraying over the nodes. And now it works. 1, 2, 3, 4, 5, 6. Now this still is not right. What's normally done is this is a module, and then end module. And now this value here, the node is returned. So this no longer takes a value. Well, it can, but this other way is the way it's normally done. So takes nothing, returns node, and then the pop does what it does before, destroy does what it does before. Now what happens is you go, let's move this out of here. So struct q extends array, implement q, and let's change this to q module, q mod, and struct. And now we can have our own values in here, whatever we want, like unit u, integer I, etc., etc. And why I had this take a node before was because the struct using this q may not use standard allocation. It may, for example, want to insert an indexed unit. An indexed unit is just a unit that has an allocated integer to it through what's called the unit indexer. So it may allocate something that's, or it may rather use a node that's already allocated. Now for now we're going to keep the allocate in here, but later on we'll probably want to remove that. So we're going to keep it exactly like before, and let's just have the read-only integer value. And now let's change this to q add and q pop. So now we can have our own add method in here. Takes integer value. Let's say read-only integer value 2 as well to show that it can be different. And integer value 2 and returns nothing. End method. Oh. So we go local. This type node is equal to qadd. Notice that it does not actually take any values. The node itself only contains pointers to the next nodes. It's just a basic queue with nothing in it. Now we do set node.value is equal to value, and set node.value2 is equal to value 2, and then that's that. That's all that needs to be done. Then for method pop, we can actually just use the plain old q pop up here. And let's just keep it as q pop. And for method destroy, we'll keep that too. So now we can add in our very own values to the queue. Since it takes two values now, we're going to do one, how about -1, -2, -3, -4, -5, -6. So now we can iterate over this and go, comma, vjass node.value2, and destroy it like normal. And we can run that, and it should display what we expect right there. 1, -1, 2, -2, etc. So now this module can be implemented into any struct to immediately turn it into a queue. Now what we can do is, let's say we want the queue to have the struct to be able to have its own create method. So we're going to go q create and q destroy. And in fact, what we should probably do is make the queue take struct instances. So we'll give it its own little private allocator, and this is the way it's done in regular programming languages. It wastes more memory, but it's better because then each struct could have a queue in it or multiple queues instead of the struct itself being a queue. So that's a smarter thing to do, and then you could just make the regular structs and then add those structs instances to your own queue if you want. So let's just keep it as it is right now because that's starting to get to be too much work. So queue.queueCreate and queue.destroy. And this is pretty standard for what's used in a queue. Now you can play around with this and change it around so that this queue just takes an integer, and that integer refers to a struct instance. And then the module can be implemented into, well, no, actually just keep it like this and get rid of the alloc and make it so that nodes are passed instead. Then someone can make their own custom queue and then pass struct instances into that. That's much more dynamic and modular. And modular just means reusability. It can be used in more cases. You want things to be as modular as possible, as reusable as possible, as dynamic as possible. That way you don't have to recode all of this every time you want to make a queue or something, because you have specific code in here. So notice that this is very bare. It just is a plain old queue. The only thing specific in here right now is allocation. So once that is taken out, then this can literally be used in any struct. Stacks are made the same way inside of modules. And then finally, we're going to the dqueue. And we're going to make a few modifications here. First, let's get rid of the alloc. We're going to make a queue dqueue properly. So we'll go dqueue create. And all this will take is this type, this. In fact, we'll just change this into a method and we'll say it's dqueue init. And since it's now taking that, we'll get rid of it. So no longer have to worry about allocation. A dqueue is what's called a doubly linked list. So it has two pointers, a next and a previous. And because it has a previous, the last variable is no longer needed, because dqueue.prev is the last one, and dqueue.next is the first one. And we're going to create what's known as a circularly linked list, a circular dqueue. And lists and dqueues are pretty much identical to each other. A dqueue just means that you can add and take from the front, and you can add and take to the back. In a linked list, you can remove from anywhere, and then you normally add to the back, but you can also add to the front or wherever you want, I guess. So linked list is just a more open dqueue. And dqueue stands for double-ended queue. So a queue that has front and back and front. So you can take from the front and the back, and you can add to the front and the back. That's all it is. A queue going one way and a queue going the other way. So now for this init, because we're going to make it circular, we're going to set next equal to this and set prev equal to this. And then no longer need to return it. So notice now, if you loop through it, you're always going to be stuck at the dqueue pointer itself. For queueAdd, we're going to change this up a bit. No longer need to return anything. Instead, it will take this type node. So let's go ahead and erase all this code. Now for queueAdd, let's say queueAdd back. So now this will add to the very back of the queue. So remember that the last is equal to this .prev, dqueue.prev. First is equal to this .next, dqueue.next. And this is inferred, we don't need it. And then all we need to do is set last.next equal node, set first.prev equal, or rather set this.prev equal node. So set last equal node, set last.next equal node. Then we're doing set node.prev equal to last. That should be pretty apparent, obvious. Set node.next equal this. So what happens here now is if the list is empty, it'll go this points, and we'll do a double point so that the node is shown to point back. They point to each other. The node points back to this, and this points forward to node. And then if we look past node, it points back to this, and so on. It just cycles through like this. So that's a circularly linked list. If you go through it, you'll end up iterating forever. So the exit when statement you normally do is you exit when the node you're on is the actual DQ itself. Oh, and we should probably change this to DQ add back. There we go. Now let's get rid of these rather useless local variables, and instead we're going to say set prev.next equal node, and set node.prev equal prev, and then we don't even need the first, as you just saw. Let's get rid of these. And now we have to reorder the code a little bit so that we don't break everything. So first we're going to do set node stuff. So we're going to link the node to everything, then we're going to link everything back to the node. In this way the pointers aren't broken, and so everything connects properly. Because if this stuff is set first, so set prev.next equal node and then set this.prev equal node, notice here set node.prev equal prev. So now the node is pointing back to itself if this was done first. So set this.prev equal node, set node.prev equal prev. Prev was set to the node, so now the node points back to itself. So that's why the order here matters. In a list that's not circular, the operation here is a bit more complicated. So that's why everyone just uses a circular linked list, because it's just these 4 lines of code here. Now for the pop, we're going to say DQ, how about remove back? So all that happens here is, in fact, we don't even need to remove back or remove front. What we can just do is at plain old DQ remove. And it just takes the node to be removed. So this equal node to be removed. Now the reason I'm doing it this way, instead of removing from the front or the back, is because removing a node from a doubly linked list is extremely easy. It's just this, set prev.next equal next, and set next.prev equal prev. So the whatever the node previous is now points to the next, and the node next now points to the prev. To have a look at it, prev node next, prev now points to next, and next now points to prev. So the node is completely removed from the middle there, and it just turns into next, or prev and next, where they point to each other. So removing is always just those 2 lines of code. Very, very simple. And that's why you never really see a remove from back or remove from front in a DQ or a linked list, because they are actually more work than just doing it this way. And I guess what you could do is set this equal to prev or set this equal to next in order to remove from the front or the back. But then you need 2 methods instead of 1. It just becomes more of a hassle. So just do it that way. For DQ.destroy is the exact same thing. You just iterate through and destroy everything. Except you exit when this. Well, you need to do a local this type node equal this. Call node.deallocate. Set node equal to node.next, and then exit when node is equal to this. Because it's a circularly linked list now, you can't compare to 0. 0 is nowhere in there. The terminator, the sentinel node, sentinel nodes are like the pointer nodes, the things that are always there and act like little dummies. The pointer node, sentinel node, is the DQ itself. And now we can go over here and we can change this into a DQ and implement DQ mod. And now we can go dq add dq equal dq create. We can just do dq create there. You don't need the thing in front of it since we're in the struct itself. And then we can do dq. Oh, we probably just, yeah, we probably want to change this variable here. So dq add, then iterating over it, and then call dq destroy. And that should work unless I have syntax errors somewhere. Let's hope not. Oh, we got rid of the allocation, didn't we? And we changed that to dq init. Okay. So local this type, this is equal, let's implement allocate. Alloc. dq is equal to allocate. In fact, what we can probably do is return this. That way we can just do this. This type allocate dot dq init. So now it's a one-liner. Oh, that was done in the wrong spot, wasn't it? Should have been done there. This would just be dq add back allocate. And now it should work. And notice I do not have an add front right now. So let's go ahead and add that really fast. Add front just adds to the front instead of the back. So node.prev is now equal to this. Node.next is equal next. Next.prev is equal node. And next equal node. So you just reverse everything pretty much. And now this will add to the front like a stack, and this will add to the back like a queue. And this will remove from either place or wherever. And really, because you can remove from wherever right now, it's really a linked list, not a DQ. But let's not worry about that right now. We'll just call it a DQ. So we'll go ahead and save that. And I forgot to rename the method name, so let's go add front. Now we'll save that, and what else did I forget? Cannot convert nothing to integer. Oh, I should probably do return this type so I can do one-liners. Return this. Return this. And now it works. If we do this again, it should do the exact, almost same output as before. Not quite, apparently. Oh, I know why. Exit when node is equal to DQ. There we go. And now it's displaying 0, 0, 0, 0, 0. So it looks like I screwed something else up here. So DQ add back. Set prev.next equal node. And set prev equal node. That should work. The values. Oh, I know why it's not working. Return node, not this. That was silly. Now it works. Exact same output as before. If we change it around a bit, we can do add front instead of add back right there. And now it will display the same output as a stack would. And right there, just like a stack. So this got added to the front, then this got added, and so on and so on and so on. And the actual operations for these, for add back, it will be NQ. For add front, it will be push. And for remove, it would just be remove. So those are the actual operations. And then for taking from the front, it's always pop. For taking from the back, it would be something weird like remove back or something. But adding to the front is push and adding to the back is NQ. So there's pretty much a well, this could really be just called a list, I suppose, with a couple of, this really is a list now at this point. And we'll just say list destroy and list init and change this around. Oh, this should probably be list mod. And it's really a circular list, so we'll do circular list mod. Now here we'll do circular list mod, and then we'll do push there. In fact, why don't we call it list NQ and list push. And list remove, and then list destroy. So here's list push, list init. So many things to change here. List destroy. Oh, and then we probably want to deallocate that pointer there. Well, no, this does it for us, so we don't need to. And really, this actually should not be deallocating. This should essentially just unlink everything. So if we want to destroy it, we'd actually have to come out and destroy it right here. So method destroy, and now we can do the deallocate. Up here, the only thing we can really have is clear. List clear. Takes nothing, returns nothing, and method. And for clearing, all you do is set this equal, or set next equal this, and set prev equal this. And now the entire list is cleared. And really, clearing shouldn't even be done up here, because then we lose all the pointer values. Well, I guess it can, so we could have a method clear out here as well. Takes nothing, returns nothing, and method, and then it'll pretty much be destroy, just moving one line of code somewhere. Set node equal node.next and exit when this node is this. So everything gets deallocated except for the main pointer variable. And then you would call clear, and should probably call list clear. There we go. So the list does not actually get a destroy then, since it does not have its own allocation, deallocation. Now, the list can have its own destroy, and that's by just making this its own linked list and then taking integers, and those integers would be struct instances, and then the structs could like make their own lists inside of them and add themselves to the list or something weird like that. But it's generally better to just do it this way to convert the actual struct into a list. Then the user can do it whatever way they like. They can do it the way I just mentioned, adding struct instances to a list, or whatever they like. And normally in a list you should be able to add the same value multiple times. With struct instances you can only add each one once, but then each one can have whatever value you want in them, and those values can be identical to each other or whatever. So it really works out anyway. This really is the standard way to do it in Jest though. But in C++ it is done the other way, where you actually have a list and you add objects to that list. And the list has its own allocation, deallocation, and its own nodes. So the list out here would just have something like a first and a last or whatever. And then you'd have another thing called node, and those would contain the actual pointers and some generic object. And the object would be determined by what's called template. So here's where you pass in the type. And this is just like regular parentheses, it's just more of a preprocessor thing. It's like a macro. But that's not supported in vjass though. It is supported in Andromeda, which is a thing for Galaxy. But nothing in Galaxy really works at the moment, and I don't recommend moving on to StarCraft 2 after this. So that is how you use DQs, queues, and lists, and that's what they are and how they work.